Hi folks, welcome back to Math with Captain Rod. I'm making this video here to help you understand how to set up an integral for a bound area here. So what we're going to do is we're going to find the area bound between minus x squared and 4 minus x squared. So in my picture, that's this stuff. Now the first thing you probably have to consider here is you're going to need the limits, right? So that has to do with where these intersect. We need the x values here. Now I've already done this work to the side. I'm going to talk a little bit about how you do it, but I'm going to let you folks fill in the detail here. But basically, we take into account the fact that the y values are the same, which means at this point and at this point, we can say that minus x is equal to 4 minus x squared. Sorry about that. Let's write it so we can read it. Minus x equals 4 minus x squared. And that's a quadratic. If you solve that for x, you'll get the two values that I have listed up here. And I put them kind of in my little language here. X sub L is the left x value, that's this one. X sub R is the right one, that's this one. Or in the language of most calculus books, those are A and B, lower and upper limit. Okay, now the next thing we do is we draw a rectangle. And you decide on horizontal versus vertical. This one, a vertical, is going to be far easier to deal with. So what I'm going to do is I'm going to draw a rectangle. It doesn't matter where. Let's put it right here. Here's my rectangle. Now, whether that rectangle has a finite width or not is kind of how you intend on setting it up. If you're going to do a numerical like use a calculator for this or use Excel or something, you choose a value for n, say 10 or something like that, and then the width of this rectangle would be some finite number. In fact, it would be b minus a over n. But what I'm going to be doing is setting this up as an integral here. So we're de facto going to be doing n going to infinity, which means instead of delta x, I'm going to call that a dx. So there's our width of our rectangle right there, dx. So we're going to imagine that being infinitely small. And another nice thing is when you do it this way, you don't really have to worry so much about how that rectangle touches the curve. Hopefully you've seen my other videos about lower bound, upper bound, and midpoint. When you do an infinite number of rectangles, all setups will converge to the same value. So it doesn't really matter. Now, the other thing you got to consider here is the length of the rectangle. That is this length right here. And I usually call that like L of x because it's a length and it varies with x. That rectangle, if you draw it over to the right, is longer. It's longer here, longer and then shorter again. So it kind of varies as you go left to right. You always do top curve minus bottom curve. So that's going to equal 4 minus x squared minus 8 minus x. I'm going to go ahead and put plus x there for that. Okay, so that's coming from top minus bottom. Keep in mind, though, that's minus a minus x. And again, that's the reason why that's a plus. All right, so now I'm going to write a little formula here for the area of that rectangle, dA. Now, it's a differential area because that rectangle is infinitely thin. And that's going to equal the length of the rectangle, 4 minus x squared plus x, times its width, dx. So again, this is length times width, area of a rectangle. Now what we want to do is we're going to be summing those all up. So in the language of integration, what we're going to be doing is summing up all the dA's, summing up all of these. All right, so when you sum up all the dA's, you get the total area. And that's going to be equal to the sum, right, or we say the integral of 4 minus x squared plus x dx. And this is a sum over x, starting at our lower x value, that's this one. That's the minus 1.56. And ending at the upper one, 2.56. And we go through, now we applying the fundamental theorem of calculus, we anti-differentiate these terms. So that's going to be 4x minus x to the third over 3 plus x squared over 2, evaluated at the following limits. Then you put in your top value, 4 times 2.56 minus 2.56 cubed over 3 plus 2.56 squared over 2. So there's the top. I'm running out of room here, so I'm going to do minus the bottom, which is this guy. 4 times negative 1.56 minus negative 1.56 cubed over 3 plus a negative 1.56 squared over 2. Okay. Being extraordinarily cautious with plus and minus signs. This term will be negative, this one positive, but don't forget there's a minus in front of all of those. And when I work this out, I've already done this, so I'm not going to go through this now. I got 11.7 when I did this. Hopefully it's right. You can double check it for yourself. So anyway, there's an example of how you use these what I call differential elements to set up integrals and calculate areas. I hope that this helps. Have a great day.